This is really just a quick history lesson, and there's just a few things really that we want to take out of this, and we'll in class go into more detail, and I'll send you out on the internet to try and find delicious photographs and schematics of some of these various important experiments. I just wanted to outline a little bit of what is going on. The actual concept of the atom, believe it or not, is very, very old, going all the way back to the ancient Greeks, who were philosophers and were often wondering about the nature of things. And the word atomos in Greek itself means indivisible, the idea that if we were to take matter and continue to break it apart and break it apart and break it apart, we would reach a point in time when we could perform no further division, and that fundamental particle then would be indivisible. You probably know more about the history of the intervening 2,000 years than perhaps I do, but as you can imagine, all the civilizations rose and fell, and not an awful lot of attention was given, really, to the scientific study of the nature of matter until all the way up into the 16th and 1700s. The Renaissance, as you're aware, then brought back into play critical thought about various things and the beginnings of scientific reasoning. But it wasn't until literally the 1800s when scientists with relatively primitive from our perspective, but sophisticated from theirs, measurement tools began to be able to do experiments that allowed them to construct theories. Remember, theories, large ideas about the nature of the world. And the father of then modern atomic theory, in quotation marks, because of course it isn't that modern anymore, was John Dalton, and his modern atomic theory then is worth our attention just to highlight some of the things that it suggested were true and to think about whether or not they ultimately are and where we are kind of today in terms of the contemporary model of the atom and the things that make up that atom. Couple of things Dalton was dealing with, and one of them had to do with the idea that as chemical experiments became more and more numerous and repeated, that he discovered that in fact the total mass of the ingredients in a chemical reaction was conserved. And so this idea of conservation of mass was fundamental to his atomic theory. Likewise, what we call the law of definite proportions, also a key cornerstone here, that the idea that atoms were being put together in different proportions to make different compounds, and that those proportions were always the same to end up with the various compounds that we made. I'll give you an example of that in a little bit, perhaps. And so the atomic theory that he formulated tried to incorporate those important ideas. The big five here, this idea that matter is composed of atoms at that fundamental level. Atom becomes then the building block, and that all atoms of an element are identical. Again, this is his theory, suggesting that every atom of gold or every atom of lead were identical to each other, but that every atom of a different element has in some way a difference that resulted. The atom is indivisible, meaning it cannot be further subdivided. We'll return to that in just a second. And it really, since Dalton was a chemist, it's tenets number 4 and 5 that were the most precious to him. The idea that atoms combine in whole number ratios, which follows, of course, from the idea that atom is indivisible, to make compounds. And this law then of definite proportions, suggesting that depending upon the proportions of the various elements, we could make different compounds with, in fact, quite different properties. And finally, that a chemical reaction was nothing more and nothing less, really, than atoms being rearranged. That bonds are broken, bonds are formed, atoms change partners, but ultimately no mass is lost, and the atoms of every element in the reactants are going to be the same as the atoms of the elements in the products. Mass is conserved, and the only thing that's happening is that the atoms are being rearranged in terms of who they are bonded to. So what do we have in terms of the structure of the atom? There was a flurry then of research that followed Dalton's atomic theory, attempting to address those various points. What we discovered in the 300 years since then is that he was wrong in a number of cases, but he was fundamentally right. Perhaps the most important milestone after Dalton's atomic theory came as a result of work that J.J. Thomson was doing using cathode ray and cathode ray experiments. I'll direct you out. You could do so now. With the internet, you can get a very clear picture of what these cathode rays are. And in the process of working with those cathode rays, Thomson was able to discover that those cathode rays had two important properties. One, they had charge, and as a result of having a charge, Thomson could manipulate the cathode ray using a magnetic or an electric field. The second thing that was startling was that those cathode rays actually had mass. You can actually see pictures out there on the internet of him and his cathode ray tubes, and how he put a little paddle wheel in there on rails, and when he flicked the switch and turned on the beam, the little paddle wheel would turn. This suggested that those particles had mass, but from calculations that both he and Millikan did shortly thereafter, they discovered that the mass of this cathode ray particle was less than 1,000th the mass of the lightest known atom, hydrogen. The enormous discrepancy between the mass of the hydrogen atom and the mass of this particle required then that they conclude in the classic scientific method that there was particles smaller than the atom. Here was one that was 1,000th the size of the atom, and it had a charge. It's also known that whole atoms are neutral, have no charge, and as a result, they have conclusive evidence that there is a particle smaller than the atom, and it is negatively charged. The negative-positive charge thing, a convention that was developed earlier in the scientific literature. This particle is named the electron, and it's impossible to overstress the importance of electrons in understanding chemical change and chemical properties. The important questions that remained then were, where is the rest of the mass if this particle only has 1,000th of the mass? And in fact, Millikan further refines that measurement to about 1/2000th of the mass. And where is the positive charge that will cancel the negative charge to make for the neutral whole atoms? And as is often the case in science, then answers produce new questions, and the new questions then become part of the experimental research. Shortly thereafter, Ernst Rutherford then, in a series of very, very exciting and ingenious gold foil experiments, is able to find the rest of the mass and the positive charge. Again, we'll go out in class and dig through some of this, and you'll see some of the setups. But essentially, the idea here was that Rutherford took heavy particles as a byproduct of radioactive decay, fired them at the nucleus of gold foil, and was able to show by virtue of the interaction between the target particles and the bullets that there was a core of the atom that was positively charged. He calls it the nucleus, but that interestingly enough, 99% of the atom is nothing more than empty space. The analogy that we use all the time is that the nucleus is a marble in the baseball stadium of the atom, the outer limits of that atom established by the electrons and their behavior, but the atom mostly empty space, and as a result, a fairly complete picture emerges of the relationship between the outside of the atom and the inside. Although it's unfair to Chadwick, the neutron was not discovered until much, much later, and we are less interested in it from a chemical perspective. Not surprisingly, the neutron, having no charge, was very difficult to find. Note that the experiments involving the nucleus and the experiments involving the electron both relied on the property of charge in order to find it, and hence the neutron was elusive, and its discovery weighted a more precise measurement for the mass of the atom, and on the basis of missing mass, the identity of the neutron is proposed and ultimately accepted. So this table then will make up, or you'll find, you can find it I'm sure out there on the internet in lots of different forms, and the crucial elements of it are as follows. The three primary subatomic particles, which you've probably heard of before, are the electron, the proton, and the neutron. We can use symbols, not surprisingly, E, P, and N, to represent these subatomic particles, and we'll play with them in a little bit. Note that charge, which is a fundamental and intensive physical property, measured in units and with a sign, negative and positive, and that the mass number is assigned based on our selection of an element to standardize the measurement of mass. Notice here then this is a relative mass of the particle, and here you can easily see how much smaller the electron is than either the proton or the neutron. You'll see how close the relative mass of both the proton and the neutron is to 1, hence we give them a mass number 1. Notice that to 2 significant figures, the number would round to 1 anyway, and so we're rarely interested in the exact mass. Obviously, the mass in kilogram is a very, very, very small number, but we'll rarely, if ever, work with the mass in kilogram units. We'll deal with either atomic mass units, AMU, or with simply numbers, integer numbers, to represent the masses of these particles. Electron, charge of -1, and essentially 0 mass. Proton, charge of +1, and a mass number of 1. And the neutron, no charge, essentially the same mass of the proton. And the two then protons and neutrons, since they are in the nucleus, often referred to as nucleons. Notice here that the size of the atom varies depending upon the number of electrons, but anywhere between 40 and 270 picometers. If an alien kidnapped you, you would likely use about 100 picometers as the average size of an atom.